Okay, so we start with the second talk. The second speaker will be Carlo Sparaciari from University College London, and he will tell us about the resource theory of work and heat. Please.
Thank you very much, and let me thank the organizer for giving me the possibility to be here and to give a talk today. Today, I would like to present this resource theory about thermodynamics, in which work and heat are placed on the same level. This work is in collaboration with my supervisor at UCL, Jonathan Oppenheim, and Tobias Fritz. So before we start with it, I would like to give you some motivation for this work. So you know that in thermodynamics, we have a system which undertakes some kind of evolution while it's coupled to an environment. And this environment has a very well specific temperature, and we used to call it a thermal reservoir or a thermal bath. Both classically and quantumly, it's usually assumed that this thermal reservoir has an infinite size, meaning that the heat capacity is infinite. We can exchange as much energy as we want, and we're not going to change the property of this reservoir. Now, in a realistic scenario, in particular when we deal with a microscopic system, it could be that the thermal reservoir has not this property. So we should consider a finite-sized reservoir. For instance, it could be that inside our quantum computer, our microscopic system is evolved as a very fast dynamics, and therefore it's just interacting with a nearby region of your thermal reservoir, and we have to account for these finite size effects. What we are going to do is to introduce a theory that allows us to describe this finite size reservoir. And we'll see how we can describe work and heat in this framework. And for instance, we can apply also to engine which exchange energy between two reservoirs which has a finite size. However, I'm talking about work and heat, and I haven't even defined them. And I would like just to give you a brief introduction, at least. Whenever we are performing some kind of thermodynamic transformation, we have that two kinds of energy flows are involved. One is a pure non-entropic energy flow, and is what we usually call work, while the other is an entropic disorder energy flow, and is what we call heat. Now, to formalize this concept, one can consider this scenario in which we have our main system, which undertake a transformation, and meanwhile is interacting with two ancillary systems. One is a pure, is a system in a pure state, and all the energy we exchange with it is what we define with work. The other is an entropic system. It has a well-specific temperature. It's described by thermal state. We'll see then what they are. And what we exchange with it, the energy we exchange with it, is what we call heat. Just to give an example, in the classical case with an infinite reservoir, the work we exchange during a state transformation is given by the difference in free energy, where free energy is given by energy minus temperature of a reservoir times entropy, while the heat is given by the difference in entropy of our main system. So this is more or less my little introduction to work and heat. I would like also to say something about what a resource theory is, so that we clarify everything about the title. So the main goal of a resource theory is to quantify how much of a resource we need in order to perform some kind of process or some state transformation. I would say that there are three main elements for a resource theory. First of all, we have the state space, so the set of all states that describe the system under investigation. Moreover, we have that we cannot act over our system with any operation we want. Maybe because we have some restriction, because it might be that some of these operations are expensive, or maybe because the law of nature forbids us for using some kind of operation. So within this framework, we have allowed operations, is everything we can apply to our system. Finally, we have free states. So within the space state, we have a subset of states which are free. No resource is associated with them. You cannot extract the resource, and to create them, you don't need to pay any resource. There are different kinds of resource theory. You can have the resource theory of entanglement, where the allowed operations are LOCC. But here I would like just to present again the resource theory for quantum thermodynamics, in which we consider thermal operation. Lydia talked about this during her tutorial. So the state space of this resource theory is just the set of all states that describe our thermodynamic system. The allowed operations are composed by these three main fundamental operations. First of all, we can perform unitary operation which preserve the energy. So we allow for a reversible dynamics in which the first law of thermodynamics is satisfied, meaning that we are not going to sneak inside some energy or remove it without properly account for it. Also, we allow for adding a thermal state, meaning Gibbs state of any given Hamiltonian at a precise temperature. The second operation is equivalent to say that we are in the presence, our system is coupled to an infinite thermal reservoir. Finally, we can forget about part of your system. You can always trace out some subsystem. As I said, the thermal states are the free states of the resource because you can put as many as you want. They don't carry any resource, so you can use them, for instance, to reduce actually the amount of resource you have in your system. Okay, let's see the main goal of this talk. What I want to do is to present you a resource theory in which we don't have this infinite thermal reservoir, which means we don't have any free states in this resource theory. We'll see that within this resource theory, quantum states are asymptotic equivalent one to the other if they share some common property. And we'll see better what these properties are. We'll also notice that this asymptotic equivalence is essentially equivalent to the passage between a microscopic description of our quantum system to a macroscopic one in terms of observable and so on. And then we'll see how this resource theory and this asymptotic equivalence allow us to represent the whole state space in terms of a two-dimensional diagram. We'll see how we can use it to evaluate things like the rate of conversion between two states and so on. Finally, we will define work and heat in the case of finite size reservoir. And we'll see what are the limitations for quantum engines that exchange energy between two finite size reservoirs. The structure is the following. We start with the framework and with the asymptotic equivalence result. Then we consider this two-dimensional diagram, this energy-entropy diagram. And finally, we consider work and heat. So let's start with the framework. What we consider here are D-level quantum systems, so qubit, with a fixed Hamiltonian. We are allowed to operate over this system with these two fundamental operations. One of those is these energy-preserving unitary operations. So again, reversible dynamics, which is consistent with the first law of thermodynamics. In particular, what we ask is that the unitary operation commute with the Hamiltonian of a system, which means not only the average energy is conserved, but all momenta of energy. It's quite a strict request. Then we can forget about any subsystem in our system. So you can notice that what we lack here is, in comparison to thermal operation, is the possibility of adding as many thermal states. So we don't have this infinite thermal reservoir with us in this scenario. This is the resource theory. Then you can decide in which framework you want to apply it. It could be in the case of a single copy of your system, but we decided to study the asymptotic limit first. So essentially, we are interested in the case in which we have many copies of our system, and the overall state is described by a tensor product of a single system state. So in this case, rho, we have tensor product of many copies of rho. The Hamiltonian of the overall system is given by single system Hamiltonians. First remark to do is that this is quite an idealization. We are in the presence of non-interacting particles, and therefore we are considering the perfect gas of quantum thermodynamics, let's say. Nevertheless, the results we get are quite interesting, I guess. In particular, what we have is this asymptotic equivalence. Given a certain system with an Hamiltonian, we have that two states, rho and sigma, are asymptotic equivalent if one of the two conditions, which are equivalent, is satisfied. So we can have, for instance, that the energy and entropy of the rho and sigma state are the same, which is equivalent in our resource theory to say that it's possible to find an allowed operation which maps n copies of rho into n copies of sigma. And what I mean with an allowed operation is that we have an energy-preserving unitary operation which acts on the n copies of a system and also on a small ancillary system. And we'll see what small means in this scenario. And with this energy preserving and this acylla, we can reach a state which is close in trace norm to the n copies of our sigma state. So let's consider some remarks on this asymptotic equivalence. First of all, I said that the ancilla is small. What do I mean? Essentially, all property of this ancilla, such as the size of it and the energy I can store in it, all these properties are proportional to a factor, which is sublinear in the number of copies of my main system, so in the number of copies of rho and sigma. Why am I asking this? Well, because we are working in the asymptotic limit, in the IID limit, and what we are interested in are quantities per single copy of our system. And we don't want the ancilla to give us too much power. Indeed, we would like that in the asymptotic limit, it just gives us a negligible contribution. Well, having the property to be sublinear in n assures us that the contribution of the ancilla when we consider single copy quantities will be negligible. Another thing is that this asymptotic equivalence is telling us that we can map one state into another if they have same energy and same entropy. So essentially, it's giving us some equivalence class inside our state space, each of them composed by states that have same energy and entropy. This is what I mean with the passage from microscopic description, so these quantum states, to a macroscopic description, so observables, energy, entropy. And also, this will allow to represent the whole state space in this two-dimensional diagram, this energy-entropy diagram that we'll see in a minute. Finally, I'm talking about energy, but if in this resource theory we had a conservation of angular momentum, the same result would apply straightforwardly. Before we consider the energy-entropy diagram, you might be interested in this ancilla, try to understand a bit better why it's there. Well, there are three main reasons why we are using this ancilla. First of all, in order to map n copies of rho into n copies of sigma, we will have to modify the probability distribution of the initial state into the one of the final one. Indeed, we need the ancilla to be there to provide a source of randomness to be able to actually modify the probability distribution. However, this map can also be not reversible. And therefore, the ancilla will provide an help also as a register. It will make the transformation reversible. Finally, it might be that even if we have a reversible transformation, this is not energy preserving. And so the last part of the ancilla will be an energy storage place where we can put the little fluctuation of energy from going from one state to the other. Since we are talking about quantum system in general, we can have system with coherence and system without. Therefore, the last part of the ancilla will work as a coherent storage system as well. Due to the fact that, well, the protocol to map n copies of rho into n copies of sigma is mainly based on the central limit theorem, like most of the things in IID limit. And all this contribution can be proved to be sublinear in the number of copies of our system, which is what we want. Well, I would like now to consider this energy-entropy diagram. What we can do is to represent the whole state space, which is this red region, inside this two-dimensional diagram. On the x-axis, we have the energy, and on the y-axis, we have the entropy. Each point here is an equivalence class of quantum state with a specific energy and specific entropy. On the x-axis, we have all pure states, and in particular, here we have the ground state of our Hamiltonian, while here we have the maximally excited state. On the boundary above this region is this curve, essentially, is given by the set of a thermal state. Each point corresponds to a precise temperature, or inverse temperature beta. On the left, we have positive temperature. On the right, we have negative temperature, meaning inverse populated states like the one you find in lasers. Something you can do with this diagram is to express the state space instead of using this representation with linear inequality. In particular, for a state to be inside this state space, we need, well, quite obviously, that the entropy has to be greater than 0, which means all states have to lie above the x-axis. And then we need the states to satisfy this family of inequality, which are related to this beta thermality quantity. So this beta thermality is nothing more than the difference in free energy between the state you're considering and the free energy of a thermal state at that specific inverse temperature beta. We can represent this inequality. They are tangent to this curve of a thermal state, and each of them is tangent to the specific beta temperature that we are considering. So there will be is a family. We will have many of them, each of them tangent in a different place. And we need the states to stay below these lines. So what can we do with this energy-entropy diagram? For instance, we can find a decomposition in terms of thermal and excited state for any state rho we want. How can we do? Well, we find the equivalence class of our initial state rho, and we select the point accordingly. Then we decide the temperature. This temperature will give a point on the curve of thermal state, and we trace a line which goes through these 2 points. We'll intercept the x-axis. Where we intercept it will be the pure state we need in order to perform this decomposition. Then we will have that n copies of rho are equivalent to a certain number of copies of a thermal state, here k, and tensor product a certain number of copies of the excited state. In order to find how many copies we need of the thermal state, we just look at the distance between rho and the thermal state, because k will be proportional to this distance. Something else that we can do is to consider rate of conversion between quantum states. So say I have n copies of a state rho, and I want to extract as many sigma states as I can. While in the meanwhile, I can also produce some garbage state. That means I can produce some state from which I cannot extract any more sigmas. Then the rate is given by the number of maximum number of copies sigma divided by the initial number of copies rho. So is this maximum m divided by n. I can geometrically find this rate inside this with this energy entropy diagram just by finding the 2 points sigma and rho in the diagram, tracing again a line, intercept the boundary of this region somewhere. That point will be my garbage state, and the rate will be proportional to the distance between rho and sigma. Okay, this is an idea of what I can do with this energy entropy diagram. Now I would like to introduce work and heat in this situation of a finite size thermal reservoir. So you notice that so far we have talked about closed systems. We didn't have any thermal reservoir with us. But if we want to talk about work and heat, we have to introduce it. And to do so, we use again the scheme we presented at the beginning, in which we are considering a big closed system divided in 3 parts. One will be our thermal reservoir, one will be the main system, and finally, the last one will be the battery, the place where we store work. We consider an initial and a final state for this overall closed system, and we will use the asymptotic equivalence in order to find what work and heat are in this scenario. In particular, the initial state of a system will be given by m copies of a thermal state at the specific inverse temperature beta 1. The state of the main system will be given by n copies of rho, and the state of a battery will be given by its ground state. I then want to map the n copies of rho into n copies of sigma. While doing that, I also change the temperature of my reservoir, and somehow I store work inside my battery. Of course, this is an example. It could be that during the transformation I need work, and so the battery will go from an excited state to a ground state. But it doesn't matter. It's just an example. And a remark, what I mean with finite size thermal bath is that the number of copies of my thermal bath, this m, divided by the number of copies of my system is equal to a constant, even though, since we are considering asymptotic, the asymptotic limit, both of them will tend to infinity. So m and n by themselves tend to infinity. The ratio between the two is constant. It means that per single copy of my system, I just have few copies of my thermal reservoir, which is, I think, what I would mean for a finite size thermal bath. Let's rewrite the initial state and the final one. And we define work, as we said before, as the energy changing inside the battery. everything divided by n, number of copies of a main system, because we're interested in quantity per single copy of my system. Heat will be the energy changing inside my thermal reservoir, again divided by the number of copies of a main system. If we use asymptotic equivalence, and therefore we ask that the initial and final state of the overall system have the same entropy and same energy, I can evaluate work and heat, and I see that they just depend on the initial and final state of my main system. So they only depend on rho and sigma. And of course also on the temperature of the reservoir. In particular, I find that work is given by the difference in free energy between rho and sigma, but this time with respect to a effective temperature or inverse temperature, beta effective, which is neither the initial nor the final temperature of my thermal reservoir. Indeed, is given by this equation here. Yes, I don't know if you can see the pointer well. And it's, let's say, an average between these two temperatures. And essentially is the correction we get when we consider the finite size thermal reservoir. On the other hand, heat will be the difference in entropy between the final and initial system times this effective temperature. If we go in the infinite case for the reservoir, meaning that if we allow m divided by n to tend to infinity, we recover the classical limit. We find that the temperature at the beginning and at the end of a reservoir doesn't change, and the effective temperature will be the same. So we can use this, for instance, for considering the efficiency of thermal engine, which exchange between two finite-sized thermal reservoirs. To do so, I use again the scheme of before with the bath system and battery, but now I replace the bath with the hot bath and the system with the cold one, because in an engine we usually need hot and cold. We perform an operation over them so that we extract work, and meanwhile I map the hot thermal reservoir into a less hot reservoir and the cold one in a less cold one. The efficiency is given by the work I extract divided by the heat or the energy that I extract from the hot reservoir. And what we find is that the efficiency is always lower than the Carnot efficiency, meaning that whenever we consider finite thermal reservoirs, our engines cannot perform an optimal work extraction, because, I guess, of the change in temperature between the initial state of the reservoirs, they were hot and cold, and the final temperature, so less hot, less cold, let's say. Okay, with this, I think we are done. Let me wrap it up. Essentially, what we did was to introduce a resource theory for thermodynamics in which the thermal reservoir was either absent or it had a finite size. To do so, we just removed the possibility of having free states. With this resource theory, we have seen that states can be classified in equivalence classes, which just depend on energy and entropy, and we have used it to represent the whole state space in this diagram. We've seen some useful, I guess, application of this diagram, for instance, evaluating the rate of conversion between one state and another. And finally, we have considered work and heat for finite-sized reservoirs. We've seen the correction that we have to that we obtain in this situation, which is given by this effective temperature. And then we've considered limitation to the efficiency of heat engines which exchange between two finite-sized thermal reservoirs. And we've seen that they are always sub-Carnot. Let's consider this now. As you probably noticed, this resource theory was quite an idealization. First of all, we were considering non-interacting particles. And then this class of allowed operation, well, they were quite powerful. We could operate over on the, also on the smallest subsystem of our overall systems, and we could do whatever we want with it, which is not really what you could do in a laboratory, I guess. So what would be nice is to make it a bit more realistic, meaning that we would like to consider the case of interacting particles and see if the result still holds somehow, and maybe to consider coarse-grained operations. Finally, for the energy-entropy diagram, we've seen some application, but it would be nice to see whether we can also represent geometrically quantity like the work and heat, or the efficiency of the heat engines. So with this, I'm done, and thank you for the attention.
Thank you. Questions, please? Here.
So you looked at the efficiency of the heat engine as like less than the optimal Carnot engine in this scheme. When you take like the order of m is the same order of n. But I think if you take like that limit of the m is like infinity, that you approach to optimal Carnot cycle. Do you know the like scaling of the efficiency, like approaching to the optimal Carnot efficiency, like in terms of the dimension of the thermal state?
Yeah, I got it. So essentially, I didn't show it. I might. So let me check if I have some slides. Ploof. Yeah, OK. So the efficiency actually that we get is given by 1 minus this effective temperature for the hot reservoir and this cold temperature. So I decided to express it in terms of the effective temperature instead of the actual dimension of my 2 thermal reservoir, because it's easier to write them down. However, you could do, instead of using this effective temperature, consider the actual size of the 2 reservoir. Since I didn't do it, I don't know what the scaling is, and I'm sorry. But I guess it might be doable just instead of solving for this effective temperature, considering this size. OK.
Okay. Well, very commonly in engineering, you have not one conserved quantity, the energy, but 3. You would have, in addition, a conserved charge and often a conserved chemical species in a battery, for example. Okay. And then you would have not one thermodynamic potential, namely the temperature, but you would have 3. You would have an electrical potential and a chemical potential too. And then it seems to me that all of your methods go through, except that the diagrams become not 2-dimensional, but 4-dimensional, and so on. And then a bunch of practical problems come into scope. For example, the efficiency of charging of batteries, which involves both electric and thermodynamic potentials. So I wonder if you're considering, just advancing into more thermodynamic dimensions.
Yeah, that's OK. I see. Well, first of all, let me say that for the purpose of a talk, I decided to present the two-dimensional diagram. But indeed, in our paper, we consider also the possibility of changing the number of particles. So it was a three-dimensional diagram. So I guess this means that, yes, we could consider multiple quantities and conserved quantities, sorry. And it certainly is very interesting to do so. Let me just say that overall, I guess the idea here was maybe we don't consider some other conserved charge, but we are interested in ultimate limitation to the efficiency and so on. And I guess that with this resource theory, which is so idealized and it gives you so much power, we could find this overall optimal, let's say, or ultimate quantity, even without considering other conserved quantity.
But just, I'll speak bluntly. So for example, you could maybe show sub-Carnot efficiency for a three potential model, then it would have a physical interpretation as battery charging efficiency. I mean, even a toy problem that could be interpreted as battery charging would have great interest to the sponsors of this excellent conference.
Yeah, for sure. It might be a good way of proceeding with this work, I guess. I mean,
some more questions? Yeah, if not, let's thank Carlo again. And